So, what calculus course are you guys in right now? What level of calculus are
Cal
you?
2.
Calc 2 currently?
And then I'm currently in engineering analysis, which is like Cal 3 and
So you're the equivalent of Calc 3.
Cal 3 and differential equation. I guess it's the engineering side of it. So I'm doing the dual degree.
All right.
So I guess that waives the Cal 3 and the differential equation.
Cool.
Which kind of is a little weird, but
Yes, no, I think it's okay. That's equivalent to me. What calc level course are you in right now, Ryan?
I'm done.
You're done, so you're through, what was your highest?
Cal 3.
Okay. You guys?
Calc 3.
Calc 3 current? Or
Like
Calc-
2 years ago.
Good. So you're Calc 3 current, or you're all done? Done. You're Calc 3, but done already, right?
Yes, but what do you mean beyond Calc 3?
Well, there's a DeFQ class, I guess you could take, and other stuff, but yeah, in terms of calc, if you're at Calc 3, it's fine. I thought it would be relevant.
Confused, linear algebra, discrete methods.
Okay. I was just, and then Cash, which class are you?
I'm Cal 3 now.
Okay, perfect. We're ready to fly. All right. Okay. So let's go ahead and pick up where, oh, I can't even remember quite where I left off last time, so let me remind myself of that. Sorry, I'm starting a minute early.
Solution for charge.
Solution for the charge, yes indeed. Let me pull that out. So we made that thing that was eta, and then we made this other thing that was xi, that was the time rate of change of eta. Good enough. All right. Okay. Okay. So I think I'm going to maybe just take that page out of there. Did I use up that whole page? I'm just going to continue on from there. Okay. So last time we were trying to calculate for the motion of a charged particle moving in a uniform magnetic field. And from Newton's second law, using the magnetic force as the only force on the particle. So to remind you of where we were. All right, so you probably have something like this. So we found the magnetic force by calculating QV cross B. And we plugged into Newton's second law in terms of the x component of force being equal to m times the x component of acceleration, the y component of force equal to the y component of acceleration, the z component of force was equal to 0. All right, so then we had these two equations that are kind of coupled differential equations. Of course, we can decouple them by picking one of them and taking the time derivative on both sides, I mean d dt on both sides, and then we can perform a substitution, and then we get a differential equation for which there's just one unknown and we know how to solve it, and we see that it is either going to be a sine function or a cosine function there. And then that gives us an expression for v as a function of time. We can meet our boundary conditions with that to actually find the constants a and b. We can integrate v as a function of time to get the time dependence of the x component of location and the y component of location as a function of time. And we can also meet boundary conditions there to find the exact functions for x as a function of time, y as a function of time, and z as a function of time. All right. But there's another way to do it, which involves a trick, which is creating a variable which we called eta, which is equal to the x component of velocity plus I times the v component of velocity. That allows us to add up those two equations, and for a single differential equation that is also soluble, which is here. All right? And when we see that expression, then we say, oh, well, this eta function must be an exponential in time whose exponent is minus I omega t, because that's what comes out front when we do a time derivative. Okay, then we talked a little bit more just about exponential functions. All right, so we're coming back here. All right. So we have our expression for eta. And now what I would like to do is, because that gave us our expression for sort of Vx plus Ivy, which is fine. But what we really want to find is motion. That means we want to know x and y as a function of time. So we defined this new thing xc, which is x plus iy, because clearly eta is the time derivative of xc. And then we could find xc as an integral of eta dt. And we can perform our integration. And we see that we get something times e to the minus I omega t plus a constant. And that's where I'm going to pick up. All right. So this is, xc as a function of time. So the first thing I do when I evaluate boundary conditions is I think about, well, what about when time is equal to 0? That's going to give me a boundary condition, xc, when t is equal to 0. Well, that's just equal to this thing out front of my exponent, which I went ahead and called c. I just went ahead and put those all together and said, okay, that's just going to be one complex constant. And here I see that it must be, since xc, that's like chi, like an x type thing. All right, at t equals 0 is x naught plus I y naught. Oh, and that must be what c was equal to. Great. All right. So what I have is this guy here. And then you might be wondering, what's this thing here? What's this b? Well, it is also complex. It is the center of the circle. So it is like x for the center of the circle plus I times y for the center of that circle. That is, in terms of the x, y components, we have that circular motion. Okay. What we are going to do is let the center of the circle occur at x equals 0, y equals 0. And so as a result, we can choose our coordinate system such that b equals 0. So we will choose x at the center is 0 and y at the center is 0 for our coordinate system. And in that case, that constant is 0. Okay, so our solution becomes that. All right. And now, if I want x as a function of time, I have to take the real part of it. All right, and so that gives me, let's see, I've got x plus iy naught times cosine of negative omega t minus, cosine of omega t minus I sine omega t. So I don't like doing that much math in my head. Hold on for just a second. So let's say equals x naught plus I y naught cosine omega t minus I sine omega t. Show my work. All right, so then for my real part, I'll get x naught cosine omega t for one term, but then I also have this I times negative I y naught sine omega t. So that gives me a positive plus y naught sine omega t. And for y as a function of time, I have to take the imaginary part of xc as a function of time. All right, let's see what we got here. We've got y naught cosine omega t. And then I've got this negative I, so negative x naught sine omega t. All right, and that is our solution. And we should probably check and see if it agrees with the previous thing. Let me check that out. Sure enough. All right, same expression. And of course, z as a function of time is z naught plus v naught z. Because it's just moving with the constant velocity in the z direction. All right, so now we've solved for the motion of a charged particle in a uniform magnetic field in two different ways in terms of mathematics. So those are two different tricks that I showed you. One is that sometimes when you have coupled differential equations, the thing to do is take the time derivative of one and hope that you can substitute from the other one and bring them together to one equation, one unknown. Another thing to do is that maybe you can add the two equations so that it becomes a single equation, which is what we did here, a linear combination of the two. All right, so tricks to keep in mind. I'm just trying to expose you to those things. All right. So that's everything from chapter 2. So I'm going to go ahead and move on to chapter 3. Chapter 3, we get to start talking about some of these conserved quantities. So we've got momentum and angular. That's going to be my sign for angular momentum in this chapter, and we've got energy in the next chapter. Okay?
Is that like an X to the line over? Is that how you do that? For your momentum? For your angular momentum?
It's an angle sign. It's supposed to look kind of like a sextant or a...
Oh.
All right. So let's talk about, we've already talked about conservation momentum, so, but you know it doesn't hurt to hear things twice. So let's just remind ourselves that from chapter 1, we learned about the conservation of momentum. And the things that I want you to know about it are that we are going to let the total momentum of a system of n particles. Your book uses a capital P for that, which is great, except when I do things handwriting, a capital P looks just like a lowercase p. So I'm going to use the subscript tot, but in terms of what your book does, it's this capital P. And so if I've got a system of n particles, that's going to be equal to P1, now these are supposed to look lowercase, plus P2, plus and so on, plus P sub n, also known as, also known as the sum, where I is equal to 1 to n of P sub I. All right? Okay. Then, if I take the time derivative on both sides, I see that time rate of change of P tot is equal to the sum over all i's of d P sub I dt, where I know from Newton's second law this is the sum over I of all the forces on each object, which I can sort of sort into sigma, sum of all external forces on object I, and sum of all internal forces on object I. Now, if I sum over all particles and I'm summing internal forces, they will all add up to 0, because for every one there will be an equal and opposite one somewhere in my sum. And so what I get is that the time rate of change of the total momentum, I'll go ahead and use the dot representation there, is equal to the sum of all external forces on every particle in my system. Okay. So that's fine. This obviously leads to the conservation of momentum, which states the following. If the net external force on an n-particle system is 0, the system's total momentum remains constant. Net external force, I'll do it in that symbol, on an n-particle system is 0, then the total momentum remains constant. And a lot of times in terms of symbols, we'll write this as P tote initial equals P tote, final at some time t, and that will hold for all times t. All right. So another thing that comes out of conservation of momentum is related to collisions. Again, collisions are things that are always assumed to take 0 time, which was one thing, but your author is kind of doubly safe and always says that they act with no external forces on them. But nonetheless, let's say that I have object 1, object 2, V1 initial, V2 initial. They happen to strike and stick together and take off at some final velocity stuck together. We call that a perfectly inelastic collision. That's the one that minimizes final kinetic energy. All right. And so in this case, if I were to apply conservation of momentum, it would look like this. P initial equals P final. Those are supposed to be capital P's. Sorry, that's a little inconsistent, but I'm applying the conservation of momentum here. All right, and my total initial momentum of my system is M1 V1 initial plus M2 V2 initial. And that must be equal to P final, which is M1 plus M2, all stuck together, moving at V final. And if you wanted to, you could solve this for V final like your author does, and you get M1 V1 initial plus M2 V2 initial over M1 plus M2. That type of thing. So that's just a walk down memory lane, I assume. But nonetheless, that's what conservation momentum is often applied to, is collisions. Another great system that we can apply conservation momentum to that's very illuminating is rockets. Now this is one that's a lot of times done in the calc-based intro. But I think it's a great example. So what we're going to think about here is, or in general, we could think about if you could imagine being in a truly isolated system so that you're like maybe floating in outer space, right? If you want to somehow get yourself moving translationally, you don't have a whole lot of options except to take whatever is in your hand and throw it in the opposite direction of where you want to go, right? So that's pretty much how rockets work. Because they can function in those types of environments. And so what they do is they just throw stuff, which happens to be spent fuel, which out the back so that they can go forward, or out the back so that they can go forward. All right. So, but even while they are doing that, we should all remember that the momentum of the total system that includes all these spent fuel, that includes everything that was initially within the rocket, will remain at 0. The total momentum will remain at 0. All right? Even though the rocket's taking off that way, the fuel's going that way. If you could add up all those little momentum of all the pieces, you'll still get 0, right? If it started from rest. All right. So in order to evaluate and get what we can from applying the conservation of momentum to a rocket, let's consider that I've got this rocket, and it's in outer space, I guess. All right, and at some time t, it has a mass m, and is moving with a velocity that we'll call v, and I'm just going to have it moving purely in the x direction, so that you could think of it as v sub x, but I'm just going to call it v. It's moving in the x direction. All right, and then at some later time, so this is at time t. At a later time, so I'll say at t plus dt, what's going on is that my rocket, all right, has ejected some amount of spent fuel this way. And as a result, its mass is that amount. Well, what should we say about that? Its mass has changed to an amount m plus dm. So it's going to have some amount of change of, time rate of change of mass. That'll be dm dt. Don't worry about the fact that that'll obviously be a negative value. We're just going to call it m plus dm. Are you okay with that? All right. So what that means is that dm, well, this guy here, which has a mass that's the absolute value of dm, which happens to be equal to negative dm, all right? Because m is going to be called the rate of change of the rocket, the rate of change of mass of the rocket. Yes, dm itself is a negative number. That's why negative dm will be a positive number. Okay? All right. So at this later time, now the rocket, having ejected this amount of mass, will now be moving forward at a rate of v plus dv. And this mass, this ejected bit of mass, will be moving. Again, I need to think about its x component of its velocity. So it's moving in this direction with a magnitude of v x, which is the speed with which these the exhausted fuel is ejected. So that's what the x is for, is exhaust, minus the v of the rocket, which is also known as v. So in terms of the actual velocity of dm, its velocity is going to be v minus vx. Because I want to just think about x components of velocity. I don't want to think about this as a component, but it's pointing in the negative x direction. So I just flip the sign on it. Okay? All right. So let's apply a conservation of momentum here. So initially, actually, it won't be conservation of momentum. I apologize. Let's just think about the momenta in each of these scenarios. I'll start with this one here. The momentum of my rocket of my rocket plus fuel system at t plus dt. Well, I'm going to try to relate it to what it was before. So and that'll be pretty easy, because I'll notice that I've got m plus dm as one part of my system, and it's moving forward at v plus dv. And then I have another piece of my system, which has a mass of negative dm, and it's moving in terms of its x component of velocity at v of the rocket minus v relative velocity of that exhaust relative to the rocket. Okay. Does everybody understand what these two terms are? Cool. I'm going to ask everybody to talk to somebody and take one moment to explain to them where that came from.
The left plus dm, that's the change in mass of the rocket.
Dakota Rodney, Cash Darcy?
Yes.
Yeah, so that's the language. I mean, it's just like you have the new momentum times the new mass times the new velocity equals
The velocity of the rocket minus the velocity of
the total momentum. And to account for the momentum that is happening away from the rocket, you just do the change in mass times that. Like it makes sense
Yeah, I know.
to me.
Yeah, right. That's all.
It wouldn't be the same as
Yeah.
It's a lot less, there's a change in the momentum. These two take some of the velocity away. You're adding
No, it's the exhaust.
What did you guys do?
Exhaust.
Subtle stuff.
And this
Yeah.
also mass times.
Subtle stuff.
Yeah, what,
This term.
so maybe some,
Yeah.
Everything's pretty
Everything's straightforward. All right, then let's go.
That is this piece that it lost. So it lost some mass.
Okay, so I'm going to go ahead and pick it up here. I would say there are some subtleties here. We've got, this is the mass of the rocket at t plus dt times its velocity plus the mass of the bit that has been ejected since t during the increment of time t, dt times its velocity in the x direction. So this gives me the x component of the total momentum of the system. All right, now I'm going to go ahead and do just the algebra. So I'm going to distribute this guy. So I get mv plus mdv plus dmv plus dmdv, which will be negligible because they're both incrementally small. So the product of the two will be negligible compared to all the other terms, or infinitesimally small, I should say, sorry. So minus dmv plus dm times v exhaust. That's the relative velocity at which the exhaust is expelled from the rocket. All right, so if I look at these terms, I see that I have a plus dmv and a minus dm times v, so those two are going to cancel out. And it looks like I'm left with three terms, except if I look at this guy, this is the initial momentum of the rocket. This is the initial momentum of my system. Because initially, the whole, even this little bit of mass is inside of the rocket and they're all moving together at v. All right, so this is the momentum of my system at time t. All right. So I see what I have here is my incremental change in momentum, which is, I'll just go ahead and be clear about this. This is the value of momentum at t plus delta t minus the value of the momentum at t. All right? And that must be equal to m times dv plus v exhaust, that's the relative velocity of the exhausted gas, times dm. Okay, so now I'm ready to say, hey, guess what? External forces on the system were zero anyway. So, since the net external force is zero, my momentum must be a constant, which means that dp must be zero. Okay. I'll write some of that out, I think. So in our scenario, this is happening out in outer space. So we have that the net external force is zero. And by the conservation of momentum, that tells me that momentum stays the same all the time, which tells me that dp must be zero. Which tells me this magnitude of dp must be zero. All right, so what I have then is 0 is equal to m dv plus the exhaust speed times dm. All right. And I need to do a separation of variables, so I'm going to write this down. M dv is equal to minus vx dm. And I'm going to just leave dv over here. Minus exhaust speed times 1 over m dm. So if this increment is equal to this increment, if I perform the integrals from initial to final for this value, it'll be equal to, if I perform the integral on the right-hand side from initial to final. So I'll go from initial to final. Exhaust speed is constant, so initial to final. Okay. On the left-hand side, I get v, which I have to evaluate from the initial to the final value. And I'll let the final value occur at time t, and I'll let the initial value occur at time 0. So that's going to give me v as a function of time minus v naught. And then I've got minus the speed at which the exhaust is ejected times 1 over m dm. What's the integral? That's right, natural log of m, that I have to evaluate from its initial value. Again, I'm going to go ahead and let that occur at t equals 0, so I'll call that m naught, to the final value that I'll let occur at t equals 2. So I've got v as a function of time minus v naught is equal to minus v exhaust, natural log of m as a function of time over m naught. And then I'll say, you know what, I don't really like this minus sign out front. If I want to get rid of this minus sign, I can invert my ratio in my natural logs argument, which is what I'm going to do. All right. And finally, v as a function of time is equal to v naught plus exhaust speed times the natural log, the initial velocity of the rocket divided by the rocket's, the initial mass of the rocket divided by the mass of the rocket is a function of time. And there we've got velocity as a function of time. And yes, you could integrate that and get x, your location, as a function of time. We're not going to do that because I think you kind of get the idea. All right. So that is an interesting application of the conservation of momentum. Again, though, I get the feeling that's probably an expression you guys have seen before, but it's just sort of reintroducing you to an old friend. So, and if not, hopefully you feel like this is a situation that you understand. So we're going to, again, meet another old friend, the center of mass. Okay, so again, we're going to talk about the case where I have a system of n particles. In that case, the location of the center of mass will be defined as 1 over the total mass of my system times the sum of I equals 1 to n of m sub I r sub I, where r sub I is the location of the ith particle. If you wanted to expand that, it would be m1 r1 plus m2 r2 plus and so on plus m sub n r sub n, all over the total mass, also known as m1 plus m2 plus and so on plus m sub n. Okay, so that's our definition of the center of mass. It's a vector equation. That means that it holds this x component equals this x component, this y component equals that y component, and this z component equals this z component. So what that results in are 3 equations. The x component of the center of mass is equal to 1 over m tote times the sum over I, m sub I, x sub I, where x sub I is the x component of the location of the ith particle. The y component of the center of mass is 1 over m tote, sum over I, m sub I, y sub I. And the z component of the center of mass is equal to 1 over m tote, the sum over I, m sub I, z sub I. All right, so in terms of finding the actual location of the center of mass, we have these 3 scalar equations or 1 vector equation that we can use. All right. Now, the thing about this center of mass is that it has kind of an interesting property. So let me just illustrate that for you now. So the total momentum of the system is equal to the sum over all the particles, individual momenta. And let's remember that momentum for each of those particles is each particle's mass times each particle's velocity. Okay, so I see that this is equal to sum over I, m sub I, r sub I dot. And then if I think about this expression here, r sub I dot, and the sum over m sub I, r sub I dot, I see that that is m times the time rate of change at the location of the center of mass. Oh, yeah, that'd be good enough. All right, so I've got this nice relationship that the total momentum of my system is equal to the total mass of my system times the time rate of change of this very specific point. And that point will be called the center of mass. And it must have been defined this way for that to be the case. All right? So that's really why we're interested in the center of mass. And I'm going to rewrite that because it is important. So this expression here is really why we'd had to define center of mass the way that it was. And the reason that we want that expression is that if I take a time derivative on both sides, it yields, well, let's see, dp tot dt is equal to m tot times the location of the center of mass's second derivative, where I see that this guy here is the net external force on my system, and that's equal to m tot times r sub cm double dot, also known as the acceleration of the center of mass. So the center of mass is a very interesting point, all right? It is the point that moves as though all the external forces, the net external force, were acting on a single point particle of total mass at that location. So that point moves as though it were a single particle, as though that n particle system were a single particle of mass m tot. That's how it moves, being acted on by all those external forces. All right, so the center of mass moves as though it were a single particle of mass m under the influence of the net external force. Is that clear? That's 3 times? Okay. All right, so this is a very important point. And I'll just go ahead and say that as this is an important point, we need to be able to calculate it not just for a system of point particles, but also for an extended object. That says, as this is an important point, we need to be able to find it not just for a system of point particles, but also for an extended object. All right. So when we have an extended object, well, it can be, a lot of different things. I'll go ahead and make a coordinate system here, x, y. Maybe I have like a length of string or wire, like that.
Or a person.
Or a what?
A person.
Or a person, that's true. Then that's going to be my third case. But maybe in the case of a string or wire, we have to think about adding up for a bunch of different bits of mass to find the location of the center of mass. So in that case, I'm going to say my increment of mass over which I'm going to sum will have the form of, well, in this case, lambda dl would be most general, but I'm just going to go with lambda dx because I've already gone ahead and let that lie on the x-plane. Where lambda will have units of kilograms per meter. It'll be sort of some length density of the object, meaning mass per unit length. If I had a two-dimensional object, then most generally I will have, oh, by the way, that should be times, yeah, no, that's good. So most generally I will have a bit of mass here that will have, that will be equal to some constant times the increment of area. So this little guy here is going to have, just like this guy here at a length that was dx, this guy here is going to have an area that's dA, and the bit of mass that's contained in that increment of area will be a constant, or just a, it could be a function in theory, but we'll call that the surface density, sigma. It has units of kilogram per meter squared times dA. And let's say I have something that's more like a person, spread out in 3 dimensions. That's supposed to look like a sphere. In that case, my increment of mass is going to have a volume of dV, and my increment of mass will be equal to rho times the increment of volume. You know, in the way that I laid it out here, it looks like my dA is probably dx dy. That's fine. The way I laid it out here, dV might be dx dy dz, or it might be something in different coordinate systems like r dr, r d theta, r sine theta d phi, that type of thing. Who knows? All right. So when we have an extended object, this is why I was asking specifically about where we are in calculus, because I didn't want to put a smackdown on anybody. But what we need to do is we need to calculate that the location of that center of mass is equal to 1 over the total mass of my system times the integral of r dm. So instead of having a summation sign, like here, instead of having a summation sign, I have an infinitesimal bit of mass, which is the dm. I still have my r. And instead of having a sigma, I have this s here, which is my integral. And I have to integrate over all the bits of mass. Okay. So, and that, it depends in terms of what dm will be, depends on how, you know, the dimensionality of your object. If it's a 3-dimensional object, you're going to use rho dv. But if it's just a flat object, you might want to use sigma dA or whatever else. So we have an example that we can do to sort of remind ourselves of how this works. And again, definitely remind ourselves of the details of the math involved. So what we're going to do is we are going to find the location of the center of mass for the cone shown with a constant, or it'll be called a uniform cone. That means it has a constant density. The density is the same everywhere. So we're going to find the location of the center of mass for the cone shown. So there's going to be a figure. And it's going to be a uniform cone, so that means that it has a density that is equal to a constant as a function of location. All right, so my figure is like so. So this cone is just flat on top. And the other things I have to label in the cone, as I'm going to call this maximum radius of my cone, I'm going to call that capital R. And the height of the cone is going to be called H. So I'm going to need my answer in terms of those things, potentially. And I think that is it. So I'm going to go ahead and start working the problem. Normally I give you guys a couple of minutes, but it's probably been a while since you guys have done something like this, so why don't I just show you how to do it. All right. So first of all, by symmetry, I know that the x and y component of the center of mass of this object is going to lie along, are going to be 0. Meaning that the center of mass is going to be somewhere along the z-axis. Indeed, if you had a uniform object that had a very symmetrical shape, like a cube or even a rectangle, whatever you call a three-dimensional rectangle, then that object's center of mass is at its geometric center. All right? So by that argument, I'm going to say that by symmetry, I know that for this object, the x component of the center of mass is 0, and the y component of the center of mass is 0. All that's left is for me to find the z component of the center of mass. I'm already 2/3 done. Okay. So, the z component of the center of mass. Let's remind ourselves that's equal to 1 over the total mass of the cone. I'm just going to use a capital M for that. Times the integral of z dm. Now, for dm, what should I use? This is a three-dimensional object, so I'm going to use this rho times dv. Oh, I still need the figure. Sorry, that's going to stay there. All right. But rho is uniform, so it's a constant. It can come out front. Now, what kind of coordinate system do you think I should use for this solution? I like cylindrical. Let's do cylindrical. So I've got rho over total mass of my object out front times the integral of z dv. So I'm going to have this increment of mass here. It's kind of hard to see. But it is going to be that dv is going to be dr times r d phi times dz. All right? So I'll go ahead and plug that in. I'm going to write it in a slightly different order, though. So, because I want to do my dz last. So I'm going to write it as dz r dr times d phi. And the reason I do that is because I always write my integrals in order. Like, these are going to be my boundaries for z. These are going to be my boundaries for r. These are going to be my boundaries for phi. Clearly, in order to get the entire cone, I have to let phi go all the way around. So that's going to be 0 to 2 pi. I'm going to have to let r go from r to r max, but r max is going to be a function of z. I can see already that r is going to have to go from 0 to r max, where r max is going to be r over h. Hold on just a second. Yeah, r over h times z. Okay. So let me go ahead and do the phi integral. Rho over m, the integral of phi gives me just a 2 pi, so that's good. Minus 0, obviously. All right. Because I just integrated phi and I got phi, which I have to evaluate from 0 to 2 pi, so I got that 2 pi there. Now I have to integrate r, except that I have r dr, which is going to give me r squared over 2. that I have to evaluate from 0 to r z over h. I keep crossing my h's, sorry, that's an h. Okay, so let's keep moving. Rho over m times 2 pi, I'm going to take the 2 from here, and I've got times the integral of z times r squared z squared over h squared dz, and z has to obviously be integrated from 0 to h to get all the mass, which is great. So I've got rho times pi over m. Any other constants I can pull up front? I've got r squared over h squared, and then I've got the integral of z cubed dz, which gives me z to the 4th over 4 that I have to evaluate from 0 to h. And I get rho pi r squared over 4 m h squared time that quantity times z to the 4th. So there's one expression. Except you know what? That's a perfectly good expression, but it is not the expression that I want, because I want to make it as simple as possible. So what I'm going to do is I'm going to notice, but m is equal to the integral of rho dv. So I think I'm going to be able to get a nicer expression for this if I find an expression for m and substitute it in there. All right. We're going to have to do that next time. Also, next time we're going to start angular momentum. I'm not assigning a new homework right now because you guys have plenty of your hands, given that there is a test a week from today. So I will see you on Friday. So these 3D integrals were done in Calc 3, correct?
Can it be here today? It's moving
That's
day,
right.
so
Yes.
and
Hold on, let me turn off the recorder.